Hello and welcome to lecture 27. We are discussing about the cascade aerodynamics. In last lecture, we started discussing about deviation angle and its importance. So we realize in line to what we have discussed about the incidence angle, deviation angle is also equally important. And we realize the incidence angle that can be 0, but deviation angle can never be 0, because that's what is a property of our aerofoil, and that's what will be giving or going to give us the deviation angle inherently for particular kind of aerofoil for our axial flow compressor. And based on Carter's correlation, we have discussed the deviation angle, that's what is depending on M parameter, it is depending on what is my camber angle, it is also depending on what is my solidity, and at the same time we have started discussing about how do we calculate this deviation angle as per our requirement. And as we have seen, based on this fundamental correlation, we can do our calculation for the deviation, but at the same time, with the enhancement and improvement of computational technology, they started visualizing what is happening near the trailing edge based on flow visualization, based on contour plots, based on CP distribution, and accordingly they are modifying the angle at the exit. Now when I say they are changing the angle at the exit, so as we have discussed, for incidence angle, what we are doing is inherently or by default we are giving some incidence angle at the design stage only. So accordingly our blades, they have been made and we have defined that as a blade angle. Similarly, for deviation also need to be considered. So when we are doing our design, that time by default this deviation angle we need to incorporate in our design stage, and based on that my blade metal angle, that's what will be decided with at the exit. So now when I say my blade it is made, that blade is made with blade angle at the entry or metal blade angle at the entry and metal blade angle at the exit. Okay, so do not get confused in sense of what we say as a deviation angle. This deviation angle we are taking care at the initial stage only during our design. Okay, we will be discussing all this in detail when we will be discussing the design for low speed compressor. We will be discussing this for high speed compressor. We also will be discussing that for contra-rotating configuration. Equally we will be discussing for industrial fan design. But at this moment we can understand we need to take care of change of incidence angle and change of deviation angle during the design stage only. Now let's move to next configuration. So here if you look at one by one we started discussing. So at the entry we have discussed about the incidence angle, at the exit we have discussed about our deviation angle. Now there is one more angle if we consider this angle, that's what we are defining as a stagger angle. So today we will be discussing what all will be the use of this stagger angle. So stagger angle, if we consider, this is what is the angle, that's what is been measured with the axial line, and line that's what is joining my leading edge and trailing edge. So here if you look at this angle what we are measuring, that's what is defined as a stagger angle. Okay, so outflow condition, that's what is mainly been depend, we have seen on our camber angle, but at the same time this stagger angle, that's what is having more impact. So you need to realize along with what we are discussing, our incidence angle, deviation angle, our camber angle, this stagger angle is also equally important. Now this the stagger angle, that's what it's basically talking about. It has large effect on flow passage area or blade passage area, and that's what is taking care of your mass flow rate handling capacity, or people used to say swallowing capacity of my compressor. Okay, so if we say my stagger angle, that stagger angle, it is given by alpha 1 dash. You can say this is what is my say original angle or the blade angle now, minus theta by 2. So that's what is been taken care. You can realize here this is what is say negative incidence angle, it may be positive incidence angle. So here it says positive incidence, so that's why alpha minus incidence. If I will be having negative incidence, it will be alpha 1 minus incidence angle. Do not get confused here, minus theta by 2. There are a lot of discussion, that's what is going on in order to consider this theta by 2 or theta by 3, but conventionally for our understanding, for initial stage of our calculation, we are calculating our stagger angle based on this equation. Okay, so this is what will give us idea what is happening in sense of our say stagger angle. Suppose if we are considering for the blade of rotor, then this equation that will be changed. In place of alpha 1 we will be having beta 1, and in line to that we will be having beta 1 minus incidence minus theta by 2. So this is what is giving us idea how do we calculate our stagger angle. So let's try to look at what all is a meaning. Now as we were discussing earlier, this is what is a line, that's what is representing my camber line. So we have defined the camber line, that's what is dividing my aerofoil in two equal halves. Okay, we can have different kind of camber lines. So one it says circular arc camber line, we can have parabolic arc camber line. Here in this case, if you look at, this is what is representing the change of my stagger angle and my M parameter. Remember this M parameter, that's what we are using for the calculation of our deviation angle. Okay, so based on my selection of which kind of blade and based on my M parameter, that's what we can go with this change of stagger angle. Okay, it says we will be having the variation of the stagger angle to be on higher side when we are considering say circular arc camber line. Okay, now let's try to look at what we need to realize in sense of stagger. People, they used to say stagger angle as setting angle also. Okay, so here if you look at, if you recall, this is what we have discussed earlier also. Now if you try to recall, we have discussed about our flow passage area as a diffusing passage area. That's what will be having entry area, and at the exit we will be having exit area. So within the blade passage we are considering our passage area as a diffusing passage area. So what we are doing, say this is what is my normal operating condition. This is what is absolutely working fine, where we are having our flow, that's what is following our suction surface and the pressure surface. Now going little greedy, if I will be giving excessive turning to this blade, it will be giving the flow separation, that's what will be happening from my suction surface. Basically what we are doing is we are trying to increase the outlet area here, and that's what we have defined as a excessive turning. And we have realized when we are having our delta beta to be large, that's what will lead to my camber angle to be large, and that's what is giving the flow separation to be happen on the suction surface. That's what is giving more chances for the flow to get separate from the suction surface. Now here if you look at the same configuration, what we have done, we have just changed the stagger angle or the setting angle such that we will be having our inlet area and outlet area, that's what is different. So when we are going this kind of configuration by giving say excessive stagger angle, then also we will be having the chances for the flow to get separated from the suction surface. So this stagger angle, that is what is very important when we are talking in sense of what is happening on the blade surface. Okay. Now here at this moment we are discussing everything in sense of subsonic aerofoils. When we will be discussing about the transonic aerofoils, we will realize this stagger angle, that's what is the main driving parameter for use of those transonic aerofoils, because that's what is managing the flow between two blades. Okay. So when we will be discussing about the transonic aerofoil, that time we will be touching this point again. What it says, like this stagger angle, that's what is having impact on flow, efficiency and stall margin. So if you consider the flow, that means what amount of flow, that's what is flowing through my blades or from my rotor, that's what is being set or adjusted by this stagger angle. Okay. So we say the swallowing capacity of our compressor, that's what is being driven by this stagger angle. Second, that's what is in sense of efficiency. If we consider say when we are having this stagger to be excessive, we have say the flow separation, that's what is happening from the suction surface. That's what will lead to increase the losses. That means this is what is decreasing our efficiency. So in order to improve the efficiency, we need to be very careful in selection of this stagger angle. Next, that's what is my stall margin. So same is the situation. So these days people, they are going little greedy, they are looking for the stall margins to be larger, and when we are looking for this stall margin to be larger, that will what will be managed by setting our stagger angles. Okay. It says incorrectly set leading or trailing edge angle may lead to premature separation and or incorrect turning. Yes, this is what we have discussed. Okay. For multi-stage configuration, improperly staggered aerofoil, that will cause the stage-wise loading, that's what will be getting redistributed. Okay. And that may lead to impact on stall margin, efficiency and flow. So this is what we can say, it is very important parameter. Let me point out here, suppose we are talking about say industrial fans. In industrial fans, my blades, that's what is remain same. They are having special kind of arrangement, what it says, the change of say setting angle, or they are changing the pitch. They are doing the pitching. Basically pitching is nothing but that's what is setting of the stagger angle. So if we recall, when we are using our wind tunnels, in order to have particular velocity at the test section, mainly we are changing or we are setting our blade angles. Not blade angles, that's what is we are changing our say this stagger angle or setting angle. Okay. Now recent developments in aero engines, there also people, they are started talking about variable pitch fans. Not much detail, that's what is available in open literature, but companies, they are working on those kind of configurations. If you recall, we were discussing about the incorporation of inlet guide vanes. So if you consider, my inlet guide vane blades are same, but what we are doing, we are changing our angle for inlet guide vanes. When we say we are changing the angle of inlet guide vanes, remember one thing, what we are doing is we are changing our stagger, and that's what was managing our mass flow rate, and that's what is helping us to avoid the situation as and when we are looking for high mass flow rate, we will be setting our angle accordingly. When we are setting our angles or say mass flow rate requirement is lower, we will be setting our angle accordingly. So this stagger angle, that's what we can say, this is what we can arrange. Okay, what that is one. Secondly, when we are doing our design, that time we are incorporating this stagger angle. So do not get confused with setting angle and stagger angle, that has similar meaning, but during design calculation also we need to set our angles, and that's what we say is a stagger angle, and that stagger angle, that's what we are calculating based on what is my inflow angle alpha 1 or beta 1, and what is my say incidence angle, and what will be my camber angle. Okay. Now, having all this idea, let's try to learn something different. Say, like aerodynamics, as this course define, it's aerodynamic design of axial flow compressors and fans. So your understanding of basic aerodynamics, that's what is very important. Let's talk about the viscous effect. It says the viscous effect in turbomachinery is arise because of development of growth of your boundary layer on the blade surface. If you look at, this is what is my blade surface, and even near the end wall region. Okay. So most of the compressor flow, that's what we say, it's a turbulent shear stress. Okay, and that's what is helping in order to adhere my flow on the blade surface even under adverse pressure gradient. So main dominating flow, that's what is say turbulent shear stress. If we consider laminar viscous effect, that's what is not dominating. So now the configuration is what is happening on my blade surface, that's what is very important. And we know the effect of this viscous or say viscous effect, that's what we are defining in sense of Reynolds number. That's what is say my inertia force by viscous force, and that Reynolds number, that's what we are calculating based on the chord of my blade. These days in recent literatures, people they are defining this Reynolds number based on the height of my blade. That's what is having some different philosophy, but we can understand what is happening on my blade surface, that's what is very important. So if we try to understand, we want or we are looking for our flow to be more turbulent on our surfaces. Let it be suction surface, let it be my pressure surface. We are looking for our flow to be turbulent. Okay. So boundary layers are the region where we are having this viscous effect to be maximum. We cannot say reduce that part, or we can say we cannot avoid the formation of boundary layer, but we can try to minimize that part. Okay. Now if we look at here, so Reynolds number, as we have discussed, that's what is correlating our viscous effect and inertial effect. So here in this case, if you look at, this is what is representing the CP distribution for C4 aerofoil under different entry Reynolds number. So here if you look at, say we are having say this Reynolds number in engine, that's what is in the range of 10 to the power 5 to 10 to the power 6. Okay, if you configure here, say when we are having this to be lower Reynolds number, we can say that's what has direct impact on the CP distribution. So when we are having our Reynolds number to be higher, our CP distribution is going higher. That means this is what is working as per our expectation. What is the meaning of that? When my blade is subjected to lower Reynolds number, there is a deterioration in the performance. Okay, so let's try to understand what is the meaning of that. What we have learned, say suppose this is what we consider as our aerofoil, and suppose if we consider my flow, that's what is striking here. What we learn, we will be having initial acceleration of the flow, that's what will be happening on my suction surface, and there may be possibility of the formation of separation bubble on my suction surface at the initial stage. So here this is what is forming say kind of bubble. We can say we are having shear layer inside, we will be having shear layer, that's what is moving outside. Okay, and that's what will be forming, say, separation bubble near the leading edge. And because of presence of that, later part we will be having early transition, that's what will be happening, and on later part we will be having our flow to be turbulent flow. So here if you look at, this is what is representing two different shape of, say, laminar separation bubble. So here if you look at, we can have, say, smaller laminar separation bubble, we can have larger separation bubble. Okay, so that's what is been extended from 10% to almost, say, maybe 70% of my cord. Okay, now when we are having this laminar separation bubble, that's what is, say, larger on my suction surface, that's what is impacting what is happening on my blade surface. Okay, and later on if you try to look at, because of formation of large separation bubble, we will be having flow separation, that's what will be happening near my trailing edge. Okay, so this is what is very important, we need to realize this part. Okay, now here if we move, this is what is one of the work, that's what has been reported by University of Cambridge, and they have worked this for Rolls-Royce. So here if you look at, these are the blades. Now we have understood near the hub region or near the end wall region, we will be having the formation of secondary flow in that particular region, that's what is defined as a end wall losses. So downstream in the down plane, if you look at, this is what is representing the loss. That loss we are defining in sense of total pressure loss. It is P01 minus P02 divided by half rho v square. So near the hub region if we look at, we are having the losses to be very high. Okay, it says almost this loss, it is 6.2%. Now in order to minimize these losses, what they have done, so here if you look at carefully, this is what is original blade, that's what is having, say, conventional leading edge. So that's what is having circular shape. So here we are having circular shape. Okay, then in order to minimize these losses, they have done their computational study. So these results are computational results. So they have modified the leading edge, that's what is having, say, elliptical leading edge. So this leading edge is elliptical leading edge, that's what it says, my flow is behaving nicely near the suction surface, and that's what will lead to reduce or minimize these end wall losses. Okay, so here we are having the losses near the hub region, that's what is going to reduce. Okay, and that's what it says, it is possible to have reduction in loss from 6.2% to 4.4%. So if you try to recall, we were discussing about what is the effect of shape of my leading edge. So here in this case, if you look at, this is what is representing my conventional, say, leading edge, this is what is my modified leading edge. They define that as a laminar flow leading edge. Now, like we need to remember one thing, this computational study when we are doing, we are solving basically, say, Rand's equation, that's what is a truncated form of full Navier-Stokes equation, where we are neglecting so many parameters, and that's what is the reason why it may not be possible for us to capture what is happening near the leading edge in sense of laminar flow. We are assuming whole our flow on the blade surface is a turbulent flow. Okay, so it demands for systematic study, that's what need to be carried out on the suction surface, what is happening. Now that's where our cascade tunnel, that's what is coming into the picture. So in order to study this situation in line to what Reynolds number we are having, what we need to do is we need to select our chord length accordingly. We will be discussing this point because this chord length, that's what is very important for our design configuration also. So in order to study what is happening on my blade surface, we will be selecting larger, say, chord cascade. Now when we are having larger chord cascade, we can capture what all minute details, that's what is happening on my suction surface, same way what is happening on my pressure surface. Now those data what we have captured using cascade tunnel with, say, recent measurement techniques, maybe PIV, we can use maybe by using, say, hot wire anemometry with flow visualization, we will be having whole lot of data, that's what will be available. Now those data that can be used for validation for the development of new turbulence models what we are using for our CFD analysis. Now companies, these engine manufacturing companies, they already have their database with them, and based on that they are taking care of all these things what is happening on the blade surface. Okay. Now this concept what we are discussing, it says by using this they are able to minimize the loss by, say, almost 30%. That's what is a big number. Okay. And the same concept, that's what they have adopted for Trent 700 EP, and they have found by incorporation of this kind of leading edge, they are able to reduce the fuel burn by 1.3%. Now this small number what you are observing, that's what we can say it is for particular one engine. There are number of engines, they are fitted with the aircraft, they are flying globally. Now if you count per year the barrel or, say, fuel consumption, that's what will be reducing a lot in that sense, and that's what will be saving of maybe millions of dollars a year. And this is where we are looking for a special attention. Okay, so you can understand this is what we are looking at, what is happening on the surface of our aerofoil. Okay. Now let's discuss here, say we are having other kind of configuration, we will be selecting our blades or, say, aerofoils that may be, say, low cambered aerofoil. We can have our aerofoil to be, say, high cambered aerofoil. We can say here my delta beta, that's what is, say, lower, here my delta beta, that's what is, say, larger. So if you capture the physics at the exit, we can have thin wake, that's what will be coming out. Here in this case for highly cambered aerofoil, we will be having thick wake, that's what will be coming out. Now what is happening? So if we consider we are having, say, highly cambered aerofoil, for that we will be having higher losses. Okay. Suppose if I consider we are having, say, thin aerofoils, or we can say we are having low cambered aerofoil, that's what will be giving me lower losses, but at the same time my lift is also lower and my work done capacity also is lower. Now here I want to introduce the loss, that's what is defined as a profile loss. So this profile loss, that's what is defining my total pressure loss, that's what is happening across my stage. Or we can say if we are calculating across my rotor, I can calculate that across my stator, I can calculate across the stage, that's what is defined by this P02 minus P01. Okay. Now this profile loss, that's what is depending on different flow parameters. So if we say that's what is depend on my Reynolds number, it depends on Mach number, say longitudinal curvature of my blade, inlet turbulence, free stream unsteadiness, and it is also depending on what is my pressure gradient and the strength of my saw. Okay. This profile loss what we are discussing at this moment, that's what is having relation for the future discussion. That's the reason why I have kept this here. Say this course as we are discussing is for design, so we are more emphasizing on the design part, this loss, three-dimensionality, aerodynamics, all this that need to be read by you in advance. Okay. If not, maybe you can go through the open literature go through the books what we have suggested, and that's what will be giving you idea what all losses we are talking of. It says it is also depending on my blade parameter, because this is what is very important for our design. It says what is my thickness of the aerofoil, what is my camber angle, what is my solidity, if there is any sweep or not, the skewness of my blade, stagger angle and blade roughness. So all these blade parameter, that's what is affecting my profile losses. Okay. So here we can say we have started discussing about our stagger angle, we started discussing about what are the effects of my viscosity or the viscous losses, then we started discussing about what is the effect of my change of leading edge on my flow physics, we started discussing about the profile losses. Okay. So with this background we are stopping here. Thank you very much. See you in the next lecture.